So in the previous lesson, we discussed the key ideas for graphing linear inequalities. We're going to take that same discussion and reapply it again today. So what we're going to do is graph the boundary line for an inequality. And when we graph our boundary line, we are looking at, is the inequality a greater than and less than, or is it a greater than or equal to and a less than or equal to? So if it is a greater than or less than, then we make the line a dashed line, indicating the line is not part of the solution. If the inequality is less than or equal to or greater than or equal to, then we have a solid line, indicating that the line is part of the solution, and we can pick points on the line in our solution set. For an inequality with a less than or equal to, we shade below the line. For an inequality with a greater than or equal to, we shade above the line. Now remember that the y has to be to the left on both of those instances. After, you choose a test point and verify that the shaded region you selected is correct. So example number 1, we're going to start by graphing our linear inequality. We'll start graphing by plotting a point at the y-intercept. So we are going to plot a point at 0, 1. And then my slope is up 3 over 2. You can also go down 3 and left 2. And then we're going to connect our points. Now, since the inequality is greater than but not equal to, we connect our points with a dashed line. And then the y values are greater than, so we're going to shade above where y is greater than. Okay. Number 2, this graph is in standard form. So we're going to start our graphing by plotting our x and y intercepts. So we'll plug 0 in for x to start, which will give me my y-intercept. And I can see that if I divide both sides by 2, when x is 0, y is also 2. And then we're going to plot our other intercept. So we're going to plot the point when y is 0. So 4x is equal to 4, so divide by 4 and we get 1. So my x and y intercepts are right here. I can see my slope is down to right 1. So I could continue that pattern now that I know my x and y intercepts. My line is going to be solid because it's equal to. So I'm going to connect my points. And then when it's in standard form like this, we can't tell based on the inequality. So we have to pick a test point. So I'm going to select the test point 0, 0. So you get 0 plus 0 is less than or equal to 4. So 0 is in fact less than or equal to 4. So therefore my test point of 0, 0 would be true. So if my test point is true, then I can shade where my test point was. Next, we have y greater than or equal to 3x. So we're going to plot our origin, which is 0, 0, because that's the y-intercept. It goes up 3 and over 1, or down 3 and left 1. It's greater than or equal to, so my line is solid. And then y is greater than, therefore we shade above. And again, you could have checked this. Now this time you cannot check it with 0, 0 because 0, 0 is on the line, so that doesn't help me determine where to shade. So maybe I want to make my test point -2, 2. So what you would do is plug in a +2 for y, and then you'd plug in a -2 for x. And I see that 2 is in fact greater than -2, so therefore my test point is true, so that means my shading is correct. Okay? Over here, once again, this isn't solve for y, so I really like to put my equations in y equals mx plus b form. So I'm going to add the y over. So I have y is less than, I'm going to subtract that -x thirds. And then I'm going to leave my y-intercept of +2. So I'm going to start my graph by plotting my y-intercept, which is at 2. And I'm going to apply my slope, which is down 1 and over 3. So kind of run off the board here, go up 1 and left 3. It's y less than, therefore my line is dashed. And y is less than, so where are my y values less than? Well, my y values are less than below the line because that's where y is less than. So we shade below. And again, you could check 0, 0. You could plug it into the original. So that would be like 0 thirds less than -0 plus 2. You could plug it into your transformed equation. Doesn't matter. Either way, we get that 0 is less than 2, which is true. Therefore, since my test point is true, my shading is correct. If I had picked a test point above the line, then I would want it to be false. Inequalities are really helpful for solving word problems that might have multiple solutions. So not every word problem has a singular solution. Say a restaurant has 15 eggs. They need these eggs to last until the next delivery. An order of scrambled eggs requires 2 eggs. An order with an omelet requires 3 eggs. So we're going to say that S represents scrambled and O represents omelet. And then we're going to write an inequality to model all the possible combinations of orders of scrambled eggs and omelets. So I need 2 eggs for scrambled and 3 eggs for an omelet. So I have a total of 15 eggs. But we could actually use the 15th egg. So it's going to be a less than or equal to in this case. And then the total number of eggs I have, which is 15. So we could plot our graph by looking at our x and y intercepts again. So if I have no servings of scrambled eggs, then I'm going to have 5 omelets. So I'm going to say that scrambled is my x and omelets is my y. So if I serve no scrambled, I would serve all 5 omelets. So that would this point right here. And then if I served no omelets, but all scrambled, that would give me 7.5. So that's going to be right here in between the two. Now we know we can't serve 7.5 sets of scrambled eggs. So we have to take into account that this inequality is really only the whole numbers in our solution set. So the slope is going to be -a divided by b. So in this case, -2 thirds. So that means it's going down 2 and right 3. And you can serve the omelets or eggs on the line. So we're going to have a closed solution set through here. All right, so what that means is the line is solid, but only points that hit totally on corners of the line will count as solutions. So this is a solution, this is a solution, and then our region isn't fully shaded. It has to be the corners of all the values inside. So this one is a little unique because you can't fully shade this because again, we know we can't have odd servings. So that kind of leads us into discussing the domain and range. So the domain and range for this type of problem is that the restaurant can make no scrambled, or they can make up to 7 scrambled. That's this point right here because we know they could really make 7.5, but we can't make half a serving of eggs. So they can make a total of 7 scrambled. And then for omelets, we go up to our y-intercept and we can say that they can make 5 omelets, and then that they can make any combination of the two of them in between. So one potential combination in the middle would be to make 1 omelet. So that would be any of these, and maybe 4 scrambled. So that would be the 0.41. You could also have the inverse of that, which is 1/4. And again, many other solutions, all those purple dots. So 25 performers of the Big Tent Circus are in the grand finale. Some pile into cars, some pile into bicycles, and all of them are in the performance. 7 performers are in each car, and 5 performers are on each bike. Draw a graph showing all of the combinations of cars and bikes that would work for the finale. If we used a minimum number of bikes and not all of them, and we used 3 cars, what would they look like? So let's start by getting our graph done. We'll say that X is bikes and Y is cars. And then we know that we have 7 performers in a car, and we have 5 performers on a bike. So 5B plus 7C has to be less than or equal to 35. So once again, let's find our X and Y intercepts. What if there were no bikes and all cars? Then we would have 5 cars. If there were no cars and all bikes, then we would have 7 bikes. Now, because when we connect these, none of those other points should be perfect points because my slope is down 5 and over 7. We would have a dashed line. I know this one here looks pretty close, but if you think about 3 bikes, that would give me 15 performers, and 2 cars would give me 14. So 15 and 14, right? 1, 2, 3, 4, 4. Or sorry, that would give me 20 3 and 3, sorry. 15 and 21, that would give me 36. So it's just slightly below that. So I could actually take down the thickness of the line, and maybe that would help see that a little bit better. So let's do that now. Let's use a thinner line to connect my graphs so you can see how none of these perfectly hit corners. And just like in the previous example with the omelets, all of the solutions have to come from those perfect corners, because you cannot have half a bike or half a car. So it says draw a graph, which would be the maximized. Well, the endpoints are going to maximize the number of performers. So the only way to use every performer is to pick an X or Y intercept. If you think about any other combination, you're going to be missing one or two performers. So the endpoints are going to be the only possible combination to use all performers. And then find the minimum number of bicycles that would be needed if 3 cars were available. So if we only now had 3 cars available, so we're saying, okay, we cannot have this many cars. So now we're maxing out our line here. It says find the minimum number of bicycles that would be needed if 3 cars are available, then determine other possible combinations. So now the minimum number of bicycles we'd want to pick is this point right here, which is 3. And then the maximum you could pick would be 6. And then last but not least, we want to write inequalities for the graphs given. So in this case, we're going to need our math symbol because the line is solid, so we need an equal to. It's shaded below, so y is less than or equal to. And then we want to talk about our slope. So it's going through the point 3, so that's my y-intercept. And then my slope is negative. It's going down 1 and over 2. So my slope would be a negative 1/2 x plus 3. Number 12, we're going to skip for now. That's an absolute value. We're going to learn about those tomorrow. So you can just go ahead and put a big X on number 12. 13, we have again a y-intercept 2, 3, 4, 5. We have a solid line and it's shaded above. So we're going to say that this time it's greater than or equal to. I also have a positive slope. So it looks like if you go corner to corner, it's going up 2 over 1, up 2 over 1. So that would be like 2x plus 5. And then last but not least, we have an inequality that's dashed. It's still shaded above, so y is greater than. And then again, my line is going down, so I have a negative slope. So you can see here, it's going down from 3 over to 2. So it's going down 1, 2, and over 3. So down 2 would be negative 2, and then over 3x, and my y-intercept is at negative 2. So you'd say negative 2/3 x minus 2. Okay, that concludes our day 2 lesson. Your homework is 2-8 graphing linear inequalities, day 2.